In this video, we are going to talk about limits at infinity. And so for a motivation for what we're going to be looking at, we're going to look at the following graph of the function f of x equals x squared minus 1 over x squared plus 1. So if you look at the graph of this function, it looks something like the following. Where we have this line that we do not cross, called a horizontal asymptote, of y equals 1. And so notice, as the values of x get larger and larger, we're getting closer and closer to this value of 1. But we don't actually reach that value of 1. We just approach it. And so this is the idea behind a limit at infinity, is this idea of approaching something as we get really large. And so we're going to let f be a function defined on some interval a to infinity. Then the limit, as x approaches infinity, of f of x is equal to L if the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. And so this is how we define a limit as x goes to infinity. And again, all we're saying here is that if I pick x to be really, really large, I get really, really close to the value of L. And so from this graph, we see that the limit as x goes towards infinity of x squared minus 1 over x squared plus 1 is going to be the value 1. Now, there's nothing specifically special about infinity in this case. Notice if we go towards negative infinity, picking really large negative values, this also happens. And so we similarly say that if we let f be a function defined on some interval negative infinity to a, then the limit as x goes to negative infinity of f of x equals L if the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large as a negative value. And so again, all that we're really saying here is if we go off to the left, getting smaller and smaller in negative values, more and more negative, then we have a limit as x goes to negative infinity. And in this case, for our function x squared minus 1 over x squared plus 1, we also see that that value is 1. Now, there are a few ways this can happen graphically. I am going to only draw them going off to infinity, but negative infinity behaves the same way. And so the first thing that we could have is we could have a graph where this is going to be a value L. We could have a graph that does something like the following. And so maybe it crosses the line L at some point, but eventually as we get larger and larger, we're just really approaching that value L. We could also have that it just never crosses that value and it just gets closer and closer, which is what we were seeing in terms of the function x squared minus 1 over x squared plus 1. And then the third possibility, so we could again have our line value L, where it could keep crossing, but as you get closer and closer to L, it stops, it keeps oscillating back and forth around L, but the waves get smaller and smaller. So it's getting really, really close to L, just it keeps crossing back and forth. You can think of this kind of like a sine wave that's shrinking in how big the waves are around this value of L. Now, geometrically, we have a name for this, as I already mentioned the name. And so the line y equals L is called a horizontal asymptote of the curve y equals f of x if either the limit as x goes to infinity of f of x equals L, or the limit as x goes to negative infinity of f of x equals L. And so if either of the limits going to be either infinity or negative infinity approach this value of L, then what we have is a horizontal asymptote. And so now these don't have to necessarily line up. So if we look at the following example, we are going to graph the function here y equals tangent inverse of x. And so graphing the function y equals tangent inverse of x, it looks something like the following. And so notice it has two horizontal asymptotes. It has one right here, and it has one right here. And so these are the lines y equals negative pi over 2 and y equals positive pi over 2. And so now this graph of tangent inverse, or it's also called arctangent, is a helpful graph to remember. And so it does have these horizontal asymptotes where they are different if you're going off to infinity or negative infinity. And so just in our notation, what we're saying here is the limit as x goes to infinity of tangent inverse of x would be pi over 2, and the limit as x goes to negative infinity of tangent inverse of x is negative pi over 2. And so this is an example where they aren't the same. Now, just as with regular limits, how we can have a limit going off to infinity or negative infinity, meaning like the limit as x goes to a of f of x could be positive or negative infinity. Limits at infinity can also go off to positive or negative infinity. And so if the function f of x grows without bound as x gets larger, then the limit as x goes to infinity of f of x is defined to be positive infinity. And similarly, if it gets smaller without bound, it goes to negative infinity. Just like the same idea as when we were just having an a that we were going to rather than off to infinity or negative infinity. And so an example graphically to keep in mind for this is if we look at the graph of the function y equals e to the x, we see that its graph looks something like the following. And so in this graph, the limit as x goes to infinity of e to the x is infinity, while the limit as x goes to negative infinity of e to the x is 0. And so we can have this situation where one of them goes off to infinity and one of them does not. So now, from a graph, it's fairly easy to identify horizontal asymptotes, so identify what's kind of happening for the limits at infinity. But we don't always have a graph. And so we want to talk about methods of computing these limits when we don't necessarily have the graph. And so we're going to use the following fact for a lot of these limits. So the limit as x goes to infinity of 1 over x is equal to 0. Now, the idea behind this is if you take 1 divided by a really large number, you get a really small number. And so you're going off to 0. As you pick x to be arbitrarily big, you can make 1 over x arbitrarily small. And similarly, the limit as x goes to negative infinity of 1 over x is also 0. For the same reason, 1 divided by a really large negative number still is getting really small. Graphically, if you look at the graph of 1 over x, the graph of 1 over x looks like the following. And so we can see we do have this horizontal tangent line of 0 on both sides. But we're going to use this fact, or rather a fact related to it, to compute limits. And so the fact that we're going to actually use is if r is greater than 0 is a rational number, then the limit as x goes to infinity of 1 over x to the r equals 0. And if x to the r is defined for all x, then the limit as x goes to negative infinity of 1 over x to the r equals 0. Now, this is just coming from our limit laws, so the limit laws still apply with limits going to infinity, limits at infinity. And so we still can use our limit laws here. And this caveat of if this is defined, this is just saying we don't want to be taking square roots of negatives, things like that. So sometimes if you try to plug an x in, x to the r might not make sense as we go to negative infinity because we can't take the square root of a negative. That's all that's meaning. The situations we'll be looking at, that's not really a concern. But just using this fact of we know these limits go to 0, we can compute a number of limits at infinity. And so we're going to look at several examples. So we're going to take the limit as x goes to infinity of 3x squared plus 4x minus 1 divided by 9x squared minus 2x plus 3. And so we want to compute this limit as we go to infinity. And so now the trick here with computing limits like this is we're going to multiply by 1 in a special way to create this 1 over x to the r situation. And so what we do is we multiply the top and the bottom by 1 divided by the highest power on either the top or the bottom. And kind of the method that I use is I just find from the top and the bottom which one's the highest, and that's the one I divide by. I multiply by 1 over that. And so here we have a power of 2 on both the top and the bottom is the highest power. So we'll multiply by 1 over x squared, both the top and the bottom. And so now if we do this, we have the limit as x goes to infinity. I'm going to distribute my 1 over x squared through. So I'm going to have 3x squared divided by x squared plus 4x divided by x squared minus 1 divided by x squared, all divided by 9x squared divided by x squared minus 2x over x squared plus 3 over x squared. Which, simplifying this, we have the limit as x goes to infinity of 3 plus 4 over x minus 1 over x squared divided by 9 minus 2 over x plus 3 over x squared. And now remember, with limit properties, we can break up limits over addition and multiplication, division, things like that. So as long as the bottom's not going to 0, we can split this up, and the bottom's not going to go to 0. So 4 over x is going to go to 0, and 1 over x squared is going to go to 0. Because, remember, we're dividing by a really large number, so they get really small. 2 over x goes to 0, and 3 over x squared goes to 0. And so we can simplify this whole limit just using our limit properties to be 3 over 9. And so we get a limit of 1/3. Now, technically what we're doing here, and I'm only going to write it out all the way once, what we're really doing here is we're saying this equals the limit as x goes to infinity of 3 plus 4 over x minus 1 over x squared, divided by the limit as x goes to infinity of 9 minus 2 over x plus 3 over x squared, which equals the limit as x goes to infinity of 3 plus the limit as x goes to infinity of 4 over x minus the limit as x goes to infinity of 1 over x squared, divided by the limit as x goes to infinity of 9 minus the limit as x goes to infinity of 2 over x plus the limit as x goes to infinity of 3 over x squared. And so this is what we're actually doing. We just are kind of shortcutting it. And each of these limits we know is going to 0 based on the fact that we know what happens with 1 over x to the r. And so we're just going to kind of do this trick I did up here normally, but we can do it using limit laws. That's what we're actually applying here. So now we're going to look at one more example with a polynomial. So we're going to take the limit as x goes to negative infinity this time of 2x squared plus 1 divided by 3x squared plus 5. So we're going to do the same trick as before. Multiply the top and the bottom by 1 over x squared again, because x squared is still the highest power on the top and the bottom. So we have the limit as x goes to negative infinity of 2 minus 1 over x squared divided by 3 plus 5 over x squared. Now this goes to 0 and this goes to 0. And so in the limit, we're left with 2/3. Now between these two examples, there is a pattern that you might be noticing. And if not, well, I'm going to point the pattern out to you. And so notice that if I just look at the coefficient on the highest power term, which was 3 and 9 in this first example, 3 over 9 was the final answer, which was 1/3. And in this next one, we had 2 and 3, and the final answer was 2/3. When it comes to polynomials, this trick always works. And in fact, we can extend it beyond just the situation that we are in. And so we have the following theorem. When considering a limit at infinity, so that just means x is going to infinity or negative infinity for a rational function f of x equals p of x over q of x. The following is true. So there are 3 parts to this. So if p of x and q of x have the same degree, so again, the degree of a polynomial is the highest exponent on it. So in this example here of 2x squared minus 1 over 3x squared plus 5, the degree of both of these polynomials is 2. You just look for the highest power. So if p of x and q of x have the same degree, then the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x equals the leading coefficient of p of x divided by the leading coefficient of q of x. And so here we're just taking the leading coefficients, which again, that is the coefficient on the highest power. And so if they have the same degree, then your limit will just be that ratio. Next, if q of x has a higher degree, then p of x, we have the limit as x goes to infinity of f of x equals 0, and the limit as x goes to negative infinity of f of x equals 0. So if the power in the bottom is the larger of the two, then they both go to 0. So an example of this, as we have not seen something like this, is if you have the limit as x goes to infinity of something like 3x cubed plus 5x minus 2 over 5x to the fourth plus 2x squared plus 1. This limit would go to 0 as the bottom's degree is the higher of the two. And third, if p of x has a higher degree than q of x, we have the limit as x goes to infinity of f of x equals plus or minus infinity, and the limit as x goes to infinity of negative infinity of f of x equals plus or minus infinity, where the sign is given by the leading coefficients. And whether you go to infinity or negative infinity. So now there is a bit of a technicality here with figuring out whether it's positive or negative. So we're going to look at an example. So if we take the limit as x goes to infinity of 3x squared plus 5x minus 1 over negative 4x plus 11, here if we look at the signs, notice the numerator is bigger. In degree, it's 2 compared to 1. And so because of that, we know we're going to positive or negative infinity. Here we have a positive and here we have a negative. And so since we have a positive over a negative, this is going to go towards negative infinity. And similarly, if you have a negative over a negative, it goes to positive infinity, positive over positive, positive infinity, negative over positive, negative infinity. It's just the usual rules for multiplication and division with positives and negatives. The trick comes in when we're dealing with going to negative infinity. So if we're going to negative infinity, if we have something like 3x cubed plus 1 over x plus 1, now what we have to be careful of is what's happening with the sign. And so what helps here is to think, what is the top going to and what's the bottom going to? And then just take the sign from there. So the top, as we go to negative infinity, a really large negative number cubed is still very negative. So this is going to go to negative infinity, and the bottom is going to go to negative infinity. But the top's going faster, and so the final answer will be negative infinity. And so if you just consider what the top and the bottom are going towards, you can figure out, by going towards, I mean, is it positive or negative infinity? You can figure out what the sign is. It's just the signs from those. With the positive infinity case, it's really just checking leading coefficients. When you're looking at negative infinity, you have to be a little bit more careful, as if I just changed one thing, well, notice in this example, I said something wrong. This is positive infinity, because you have negative over negative. But if we just change one thing and write a negative instead, so we have x to the negative infinity of 3x cubed plus 1 over, say, negative x plus 1, now we have that this will go to negative infinity because the top goes to negative infinity and the bottom's going to go to positive infinity. And so you just have to watch your signs there. So the next thing we want to talk about is we want to talk about when we're dealing with radicals. So we can still take these limits when we are dealing with radicals. And so we want to look at the limit as x goes to infinity of the square root of 2x squared plus 1 divided by 3x minus 5. And so when we're dealing with radicals, the trick is to factor out the highest power from the numerator, or from the radical, and then use that with the same properties we were doing before. So to see this, this is the limit as x goes to infinity. And I'm going to factor out an x squared, because that's the highest power from under the radical, from everything under the radical. Now I want to pull this x squared out of the square root. So pulling the x squared out of the square root, we have the square root of x squared times the square root of 2 plus 1 over x squared divided by 3x minus 5. And now the square root of a square is something that is important to remember. And so the square root of a square equals the absolute value of x. And so if you plug a positive number in and square it, you get out a positive number, and then you take the square root, so you get back the original. But negative numbers, when they get squared, go to a positive, and then the square root function always returns a positive. And so you don't get out the right thing, you get out the negative of it, or the absolute value of the negative. And so we're going to take the limit as x goes to infinity of the absolute value of x times the square root of 2 plus 1 over x squared divided by 3x minus 5. Now notice we're going to positive infinity. Since we're going to positive infinity, we're only really caring about positive values of x. So in this case, the absolute value of x just equals x. So we don't really have to worry too much. In this case, it's just going to be positive x. Now, once we have factored out the square, out the x squared part, now we're going to do the same trick that we did before. So we're going to multiply the top and the bottom by 1 over x in this case, because that is the highest power on the top and the bottom. And now on the top, that's just going to cancel with our x that we pulled out, so we're left with the square root of 2 plus 1 over x squared. Now on the bottom, we're going to get 3 minus 5 over x. And so this then equals the square root of the limit as x goes to infinity of 2 plus 1 over x squared divided by the limit as x goes to infinity of 3 minus 5 over x. And so doing our trick from before, 1 over x squared goes to 0, 5 over x goes to 0. And so we have left with the square root of just 2 over 3. And so that's the final answer. And so we get the square root of 2 over 3 as our limit in this case. Now, remember that we were going with x going to positive infinity. If we change this problem just slightly, and I'm actually going to do a different problem, but we're going to change things slightly. Now we're going to go to negative infinity. And we're going to look at 3x plus 2 divided by the square root of 4x squared plus 8x minus 1. Okay, so now, in this case, we're going to do the same thing. We're pulling stuff out of the radical on the bottom now, though. So we have the limit as x goes to negative infinity. We're going to leave the top alone. We're going to factor an x squared out. You factor the highest power out of the radical. So we factor x squared out, and then we have 4 plus 8 over x minus 1 over x squared, which becomes the limit as x goes to negative infinity of 3x plus 2 over the square root of the square of x squared times the square root of 4 plus 8 over x minus 1 over x squared. And this becomes the limit as x goes to negative infinity of 3x plus 2 divided by the absolute value of x times the square root of 4 plus 8 over x minus 1 over x squared. And now this is where it becomes relevant that this is the absolute value of x, not just x, when we take the square root of the square, as now we're going towards negative infinity. And so we're plugging negative numbers in for x, so the absolute value of x will become negative x. That's just the definition of the absolute value function. So this becomes the limit as x goes to negative infinity of 3x plus 2 divided by negative x times the square root of 4 plus 8 over x minus 1 over x squared. Now we're going to do the same trick as before. We're multiplying the top and the bottom by 1 over x. And so this becomes the limit as x goes to negative infinity of 3 plus 2 over x divided by negative square root of 4 plus 8 over x minus 1 over x squared. And seeing where things go to 0, 2 over x goes to 0, 8 over x goes to 0, and 1 over x cubed goes to 0. And so in this limit, we're left with just 3 over negative square roots of 4, which is going to be 3 over negative 2, which is negative 3 halves. And so we got out negative 3 halves here. Now, the big thing to keep track of is the fact that this negative sign came from the fact that we were going towards negative infinity, because the absolute value of x became negative x. And so it's important to keep track of if you're going to positive infinity or negative infinity when we are dealing with roots. So now we want to look at the following example. So we have the limit as x goes to infinity of the square root of x squared plus 1 minus x. So here we have this difference of two things that are both getting really large. So what we're going to do is the same trick that we did before in computing limits when we had a radical plus or minus something. That is, we're going to multiply the top and the bottom, which the bottom in this case is just 1. We're going to multiply the top and the bottom by the conjugate of our expression. So we're going to multiply by the square root of x squared plus 1 plus x divided by the square root of x squared plus 1 plus x. And so multiplying by the conjugate, we've seen what happens before in the top, so I'm going to do it a little bit faster. But we have the square root times the square root, so we're going to have x squared plus 1, then minus x squared on the top. And on the bottom, we're just going to get our conjugate, which is the square root of x squared plus 1 plus x. And this simplifies to give us the limit as x goes to infinity of just 1 divided by the square root of x squared plus 1 plus x. Now what we're going to do is we're going to notice that we have this square root of x squared plus 1 is as x gets really, really big, this piece is going to get really big. So that's going to go towards infinity. And x, we've already said, will go towards infinity. So we have 1 over a really large positive number. So this is just going to be 0. And so that gives us our limit in this case. So now the last example we want to consider is not even really fully an example. But if you take the limit as x goes to infinity of something like sine of x, remember sine of x's graph does the following. It just oscillates between 1 and negative 1. And so as we go off to infinity, it's still oscillating. And so because the graph of f of x is still oscillating, in this case, we have that the limit does not exist because we don't approach a number. So the limit as x goes to infinity of something like sine of x does not exist. And again, that's because we're just oscillating between values. So just like with limits going towards some finite number, We could also have limits ad infinity that don't exist as well. We'd also have something like the limit as x goes to negative infinity of sine of x also would not exist. And that is all for this video.